All right.
Ready, of course.
Hello, everyone, and welcome. So today, I think all of you are hoping to learn about kind of applying best MLOps practices to building your machine learning applications. So first thing that I'll do before kind of our plan for today is for about like the first, let's say 25 minutes to half an hour, we'll do a presentation kind of doing we'll talk about everything that I'm going to present. And then after that, we'll continue with more of a live kind of demo side of the presentation. Actually, before we jump into the slides, I'm going to do a small thing and sort of like a teaser. So we're going to go to this studio product. I'm not going to explain what I'm doing. I'm just going to do it right away, and then we'll come back to it later. And
Maybe you can make it larger, the screen,
yeah.
the font.
Is that good?
One more time, maybe?
Okay.
Yeah, like that.
Right. So I'm just gonna change this parameter and let's see. Or let's change it to 30. Again, I'm not expecting you to understand what's going on right now, because like what I'm doing right now will take quite a bit of time to execute. So I'm doing it at the very beginning, and then we are going back to our slides.
I'm really intrigued now.
Yeah, that's the point. So as an example, project that that I've chosen today is going to be a computer vision project. There are a few reasons why I've chosen that, because kind of quite a bit of my background is in computer vision, but also computer vision projects and in general, like deep learning projects, are notoriously hard to execute because of the long training times, infrastructure that's needed to train these models, and kind of all the experiment management, like the data sets that typically those projects require are pretty big. So there's a lot of complexity in machine learning projects in general, but in projects that involve deep learning or computer vision specifically, there's a lot more of those. So we'll cover basic computer vision kind of challenges. I'll give an overview of the demo solution. We'll talk about data versioning, machine learning pipelines, and experiment management. We'll also learn how to leverage continuous integration and continuous delivery practices and cloud resources, well, if you have access to those. So this is kind of an obligatory slide that I'm sure many of you have seen before. It shows a typical life cycle of a machine learning project, where you start with you define the problem, you collect your data, start on basic model exploration and model refinement. And then when you have more or less like a model that you're satisfied with, at least like version 0, you go to like deployment integration, then you monitor and maintain that like entire application that where you have machine learning model kind of at the center of it. And then you kind of rinse and repeat. So this is our example problem that I'll be using today. So we have a data set. There's a link in the README file of the GitHub repo that Alexi shared, but it also listed at the bottom of the slide. So it's fairly simple, quote unquote. It's a data set of images of surfaces of magnetic tiles used in like engine. So these magnetic tiles are used in like engine production, so kind of a critical component. The data set itself was collected and shared by Chinese researchers, I think in around 2018. And they also manually labeled defective areas, which you can see in the bottom row of the images. So basically, if you see any white areas, those are defects, which like in an ideal scenario would need to be like automatically detected and dealt with. So it's essentially an image segmentation problem. And this is like a potential solution that we could propose, where we have some kind of web API service that would accept an input image and like do some data pre-processing, run this pre-processed input through the model, and then output a segmentation mask. So the same link that Alexei shared to the GitHub repo, it's accessible at this shortened URL, bit.ly end-to-end-cv. Okay, so now let's quickly talk about challenges of computer vision projects. So first, there's data management. Typically, the collection, labeling, storage, and versioning of this data is not trivial because of its size. Then there's model training and compute that respectively require kind of specialized expertise and specialized hardware to train computer vision models. And finally, there's deployment management, which is about like dependency packaging, scaling, and monitoring. This talk is mostly about the first 2 points, but I will touch on the deployment point as well. And I know there was a question about like monitoring, which is obviously is very important. But I'm not going to go into the monitoring part in this talk. We just don't have enough time. All right, so here's an idea that I'd like to propose. Kind of the overarching idea for the whole talk today is to leverage Git-compatible ecosystem of tools. And this idea comes from 2 underlying principles. The first principle is thinking about MLOps as GitOps for machine learning and not reinvent the wheel. And the second principle is preferring building blocks over all-in-one platforms. Kind of for your own flexibility, the building blocks must be such so that they can be integrated together and swapped for other blocks if needed. And we're going to start with the first kind of open source tool that is available from Iterative ecosystem, which is TPI, Terraform provider Iterative. And this tool allows you to kind of start prototyping. So imagine like, think about that project lifecycle that we've seen before. So in the earliest stages of your project, when you just have the idea and the data set, and you need to start like exploring potential avenues, different like model architectures and so on. So you probably don't want to do it on your laptop if you have a large data set and you're using and you're training a deep learning model. So you want to leverage some potential like cloud instances with GPUs. So this is something that TPI allows you to do. And here, let's take a look at a quick demo, and then I'll show you kind of what it looks in real life. So it's fairly simple. Once you define your script, I'll show you what that looks like. You just run Terraform apply command, and that starts provisioning resources in the cloud. And then when it's done, TPI can spit out basically a command line that will launch your IDE. In my case, it's VS Code. Using a remote interpreter in the cloud. In this case, it's an EC2 instance in AWS. So I'm gonna pause here. So if you note, like at the bottom here, it shows that I'm SSH'd into, so the interpreter that I'm using is actually from a remote machine. Now I'm checking for NVIDIA drivers, but they're properly installed. So NVIDIA SMI command runs fine. So I can see that I got a Tesla T4 GPU. So, and I can basically start exploring. I can run like Jupyter notebooks from VS Code and basically leverage GPU hardware in the cloud. Any questions so far about this before we?
When can I see this in action? I really want to.
Yeah,
do you want to show it right now?
We will see it in action.
There are no questions right now. I don't see any questions in live chat. So if you have any questions, ask them in the live chat, and will be covering them as they appear. Yeah,
Okay.
but I'm really curious to see what the Terraform script looks like, because it looks really cool.
All right. Yeah, let's move on. Okay. So now I'll talk about DVC. Probably most of you already, like, at least have heard of DVC, which stands for data version control, but actually it's a lot more than that. Like, yeah, it does allow you to version your data, which is really cool, but it also allows you to create machine learning pipelines and allows you to manage your experiments. And this open source tool currently has around 10,000 stars on GitHub, if I'm not mistaken. And we'll start with kind of machine learning pipeline. So at the very beginning, like most people, I would start with experimenting with Jupyter notebooks. And I ended up with a pretty common scenario of having like several notebooks that do different things, one for data preprocessing, one for model training, and one for model evaluation. So I could do all three things in one notebook, but that would become even more unmanageable. And let's quickly summarize a couple of things that are easy to do in Jupyter notebooks, as well as things that notebooks were not designed to do. So it's trivial to iterate on small units of code inside notebook cells and visualize ad hoc results, such as print out values of different variables or create plots right inside the notebook. What is not trivial is versioning code changes inside the notebooks, like also using IDE features and unit testing individual pieces of code. I mean, there are projects that try to alleviate some of those issues, but they don't really solve them. And on the other hand, we have ML pipelines. So what are they for? When should one prefer creating ML pipelines over writing more code in notebooks? So, well, it turns out that these toolets are flipped between two technologies. As a general rule of thumb, we tend to use Jupyter notebooks in the earlier stages of ML projects because during those early stages, we typically work on proof of concepts, and we need to quickly iterate on different algorithms and data preprocessing techniques. But once we've identified the most promising idea and we need to explore it in a more disciplined way, let's say, it's a good idea to refactor your notebook code into a machine learning pipeline. And by discipline, I mean things like tracking code and configuration changes with Git, be able to quickly refactor and reformat your code with IDE features, like writing unit tests, and it can finally make sure that every change to your pipeline components give you fully reproducible results. So once my proof of concept was more or less complete, I refactored the notebooks into self-contained Python modules for data loading, data splitting, model training, and evaluation. Each module is callable from command line. These modules will be individual stages of our machine learning pipeline. We just need a way to define dependencies and outputs of each stage so that the dependency graph of the pipeline adheres to what I have on the kind of right side of this slide. The dependency graph is key for reproducibility for two reasons. It will tell DVC in which order to run different stages. And secondly, DVC won't be rerunning a stage if nothing changed about its dependencies or outputs. For example, at first, because remember, we're dealing with image segmentation problem. So there's like several common metrics that are used. And at first I used intersection over union, IOU metric, to measure the performance of my segmentation model. But then later I decided that given the properties of my data, that maybe dice coefficient is a better metric. So if I wanted to add or replace the metric that I use in the last stage of my pipeline, there's absolutely no reason for me to run earlier stages of the pipeline, right? Data preprocessing or training, like it's still going to result in the same model. So I don't want to waste my time, especially if I'm paying for those computational resources. Optionally, we can even add a stage that checks if there are any changes to my environment, like Python environment, for example. It would write information about all the installed packages along with their versions into a requirements.txt file. And if I make and I can make all other changes, all other stages of the pipeline depend on requirements.txt. So if something changes about my environment, like DVC will know to rerun all stages for reproducibility's sake. So how do we create a pipeline? So creating a pipeline is as simple as creating a YAML file. Like by default, DVC would expect a dvc.yaml in your repository. And then in that YAML file, you define different stages, as I mentioned earlier. And the stage consists of dependencies. Well, primarily consists of a command that you tell DVC to run. And then it can, then you add dependencies and outputs for each stage. What you list as a dependency or an output affects the dependency graph. So now let's talk about kind of data versioning. So everything that you define as a dependency on or an output in the pipeline automatically kind of DVC automatically takes care of versioning those artifacts. And here on the diagram, you can see kind of roughly how DVC approaches versioning. So this way, kind of your team members can, for example, like they already run git pull and push to basically share code and collaborate on code within the team. But with DVC, your team member can run essentially git pull followed by DVC pull. So this way they get both code and data, and they get the exact same version of the code and data that you used to run your experiment. And another kind of cool feature of how DVC performs data versioning is that it also performs deduplication of identical files. So if we add a few images to our data set, that essentially creates a new version of the data set. And the size of the new version will be equal to the size of the newly added images, but not the entire size of the new data set, which is kind of more storage efficient. So this summarizes kind of the data versioning features of DVC. Now let's move on how you basically would do that and look at the demo. So here I have 3 notebooks that I talked about earlier. They do pre-processing, training, and evaluation. And I refactor them into like different Python modules: data loading, data splitting, training, and evaluation. So this is the DVC YAML file that I talked about. So you define a command, dependencies, and outputs for different stages. And you can basically run your pipeline. So here I'm running command DVC repro to reproduce my pipeline. And first in the video, you see that because I ran this pipeline earlier, DVC just told me like that it's keeping that it's keep running all the stages because there were no changes compared to the previous run. But if I change the parameter and I rerun the pipeline, DVC automatically detects this and only runs the relevant stage of the pipeline. So now let's talk about experiment management. So with DVC, DVC allows you essentially to think about experiment management as experiment versioning. And by experiment versioning, we mean that you can literally version everything, like your code, your data, and your parameters in order to like be sure that you can reproduce the exact same conditions that you ran that experiment in. Like you can return to the same experiment like weeks or months from now and get the exact same result. And to help us with experiment management features of DVC, just recently, Iterative released VS Code extension for DVC. So, in just kind of a brief sneak peek into like what it allows you to do is you can create like different experiments. So far, like what you see here in the video are the 2 experiments that I ran before. And you can create new experiments by choosing what parameter you want to change. And DVC reruns runs a new experiment with a modified parameter. And there's several things that are nice about this. So you obviously have like the table to compare your metrics, parameters, and so on. You've got your visualizations, which are fully customizable, like loss functions, metrics, how they change with every epoch. You can obviously sort by whatever metric you care about. And if you generate multiple metrics, figure out which one you want to persist in your Git history. You can easily apply it to your workspace, give it some kind of commit message. So this is kind of slightly different way of thinking, I guess, compared to how some of you kind of treat your machine learning experiments. In this framework, when you apply kind of GitOps approach, your experiments become your Git commits for full reproducibility. They're all the artifacts needed to version your data, to version your code and your parameters. And the other nice thing about this combination of kind of DVC experiment management features with DVC extension is, compared to all the other solutions that are available right now, this does not require you to have an external database to basically send your experiment metrics to like some third-party service to visualize them. Like all of that is done kind of locally. Well, in this case, when I say locally, it's local to that cloud machine that I'm running all my experiments on. All right.
There are a few questions. These questions about comparison of DVC with other tools. I'm wondering if you want to take them now or maybe.
Yeah, before we switch to the next tool, let's go through those questions. Sure.
Yeah. So the question, the first one, yeah. So they are all quite related. So the first one, I think it's about DVC. Does it conflict with other tools like MLflow?
Oh yeah, I see there are 2 questions related to MLflow. Yeah. Right. I mean, it doesn't, I wouldn't say it conflicts. Like to some degree, there is a very large like overlap between the sets of features. But with MLflow, you either have, like, I think you have 2 choices, right? You can either go with managed Databricks solution. So basically you pay the money, they spin up all the services, they manage all of them for you, and you just use it. Or you can use the open source version and maintain all the databases and services yourself. So, well, that's fine. For what I heard from a few people who've used MLflow is that if they run a lot of experiments, that quickly becomes like overwhelming in terms of like their dashboard gets like polluted with like hundreds and hundreds of their experiments. So it's harder to make sense what's going on. Here, like, let me go back to this view. What I've shown you is that, yeah, you can also generate tons of experiments. And basically, instead of like the 3 ones that I'm showing you on the screen, you can generate like 100. But you can quickly decide that there's only a few that you like and you want to persist in your Git history and then discard everything else. So basically, this framework kind of forces you to essentially clean up after yourself every once in a while so that you only persist the experiments that you like.
So this is shareable, right? So this is all the experiment results are in Git. So it's not like they're just in my VS Code. Everyone in the team has access to them, right?
So what you're seeing right now, those we would call them like ephemeral experiments. They are local to that machine that you're working on. They're actually, like, for those who are interested, let me actually post. Give me 2 seconds. I can find a blog post that describes kind of how these experiments are done behind the scenes. For those who are fans of Git, they might appreciate kind of the implementation. So those experiments are handled through Git references. So until you decide to commit them to your Git history, they're not accessible by everyone else. But that's actually by design, because you don't want to share your experiment, all your experiments with everyone. You want to share only the particular ones. So it's up to you to decide. And typically you just figure out what metric you care about most. You sort by the value of that metric and decide which experiments go into your Git commit history.
But in principle, you can use both MLflow and DVC, right? So there is another question, if it's possible to marry DVC and MLflow, which I guess means that you use DVC for versioning and pipelining, and then you actually use MLflow for experiment tracking.
Yes, that's again goes back to the what was that, the second principle, right, that I talked about earlier, is basically modularity of tools. So yeah, you can use like DVC for, like, even though it has like 3 separate sets of features, as I mentioned, you can use it for data versioning only and use like some other tool that you prefer for like experiment management or something else.
Okay, and then there is a related question to the data pipelining component of DVC, and how does it compare with other orchestration tools like Prefect or Airflow?
Right. So DVC pipelines are like serve a more, like, those are general pipelining tools, and they obviously have kind of more functionality that DVC pipelines do not support. For example, like in Airflow or other pipeline tools, you can set like a schedule, sort of like a cron job, right? I want to rerun this job on a particular schedule and what have you. So DVC does not do that. It's a command line tool. I mean, if you want to sort of write a separate cron job to rerun your pipeline, you can certainly do that, but it's not part of DVC pipelines.
So it's like Make, but maybe a little bit more complex, right?
Yeah, exactly. And there's no UI for DVC pipelines. Again, like DVC is a command line tool. So it's more, I would say, in general, DVC pipelines are more lightweight. It's much easier and faster to kind of create a pipeline. And another benefit of it being a command line tool is that you can integrate it as part of your kind of DevOps like deployment practices in general. And we'll take a look at that kind of after the slides. Are there any other questions?
Yeah, but I think if we cover all the questions, we will not have time for the actual demo, but I want to see it. So yeah, maybe let's keep the questions a bit
right.
later.
So final tool for today, so CML, which stands for Continuous Machine Learning, another open source tool by Iterative, has about like 3,000 stars on GitHub. And it allows you to kind of enable Git flow for machine learning. It has like auto reporting features for like pull requests and like merge requests in GitHub or GitLab or Bitbucket. So the idea that you can post like whatever customizable reports in your, like as your comments in either GitHub or GitLab. And it kind of seamlessly integrates with cloud services such as AWS, Azure, Google Cloud Platform, or Kubernetes. So CML integrates kind of as into your CI/CD pipelines. And let's take a look at a simple and fairly typical CI/CD workflow. Like an engineer makes some changes in an IDE like VS Code, pushes them to a remote Git server, right, like GitHub, which in turn triggers a job in some kind of CI/CD tool like GitHub Actions. And there could be like multiple configurations defining tasks to do all sorts of things depending on, for example, which branch changes were pushed to or which tag was created. So that's kind of up to you and how you prefer to work. And you can have like different CI/CD workflows. Like if you push to an experiment branch, it could trigger a task that simply reruns the pipeline, saves the resulting model metrics. And on one hand, if you push to on the other hand, if you push to the main branch, it would trigger like a completely different task that might, for example, run all unit tests, pull artifacts like a large deep learning model from a remote storage, and finally build a Docker image, deploy it to some other service. Like in this project, like the deployment service that I'm using is Heroku. And here's how you would create a workflow file. In this case, I'm using GitHub Actions, but in like other CI/CD tools use like a very similar format where you define different steps of your workflow. For example, the first part of the workflow is where I ask with like a simple command for CML to launch a cloud virtual machine in AWS. And I don't know if you can see it on the slide, I provide some options like Cloud Spot, saying that I actually want to save money on this. So I want you to launch a Spot instance instead of a dedicated one. My cloud is AWS. I want to launch my machine in this particular region, US East 1. The instance type that I want to use, so I can specify that as well. In this case, G4DN X large is a fairly cheap GPU instance. I think it's around like 40 cents an hour, but it has like 16 gigs of GPU memory, and you give it a label. So this is not required for you to run CI/CD jobs in general. Like people who've done that would attest. But the reason I'm doing this is because GitHub Actions, at least at the moment, do not provide GPU runners. So if I want to train my machine learning models on a GPU machine, I have to leverage like some external infrastructure outside of a runner provided by a CI/CD tool. And then in the next stage, I'm saying that I want to run the stage on the machine that CML provisioned for me. And there I can basically reproduce my experiment, basically run the pipeline and push my metrics and reports. So in this case, with DVC pool, I'm basically bringing all the data to that runner, to that cloud runner. I rerun my experiments. All the artifacts that got generated, I'm pushing them back to the remote storage. And then I'm creating a report that looks like this. So in GitHub, I can either under every commit or a pull request that I create, I can post different types of reports that are fully customizable. It can be a table with metrics. I can display a few kind of example images. In this case, the images that you're seeing are basically at random, like a few test images that are picked at random and ran through a segmentation model. So you can see on the first image is the input image. The image in the middle is the ground truth, and the image on the right is the segmentation mask, which is output by the segmentation model. So here's a quick sneak peek into kind of how those CI/CD workflows in GitHub Actions would work. Again, like launching a GPU runner in the cloud. And then there's a section simply configuring kind of credentials to my remote storage, as well as installing dependencies. Like in this particular project, people who already checked out the GitHub repo, they'll notice that I'm using pipenn for environment management. So now when let me actually backtrack and show you. So earlier I showed you that you can create multiple ephemeral experiments and only persist like the ones that you like. So here I just applied one of those experiments to my local workspace and pushed that commit to GitHub. That triggered a CI/CD job. So there's two stages: deploying the runner and training the model. So here I can go to this commit and see everything that is associated with that particular experiment. And that experiment is also accompanied by a human readable report. So you can check all the metrics and do some sanity check on a few random test images. And in my mind, at least one problem that it solves is that probably many of you who've worked on like machine learning projects been in a situation where you make some configuration change and you create a pull request, basically saying like, oh, I tuned these parameters, now the model performs better. And then the reviewer of that pull request might ask you like, oh, can you like provide some evidence, some proof that you actually did that? And then you start searching for like, you start posting screenshots, you start posting links to some external experiment tracking tool. And then people need to verify that that experiment actually corresponds to the changes that you made. So automatically posting reports kind of completely removes that whole process, like that communication overhead that is needed, because now, because this report is posted from inside of CI/CD job, like people can trust you that, well, the changes that you made, they actually correspond to those metrics. Actually, let's take a 2-minute break for questions here. And if we have any questions about like CML.
Yeah, we do. So one thing was related to ML flow. So it wasn't, I don't see any questions related to CML. So
Okay.
should we, because I'm thinking I really don't want to spend too much time on questions if it is up time for the demo.
Yeah,
so maybe
yeah, we'll have more time for questions later. So
yeah.
Now I want to show you kind of the like the only commercial product that Iterative has is Studio. It's essentially like a place where the like all the open source and free tools come together. And Studio is focused on like collaboration between team members when you basically experiment on your models and you need to like show progress or share your results with other team members. So firstly, like you can see on the dashboard, once you connect your repository from like GitHub, GitLab, or Bitbucket, Studio will automatically parse all of the information that you have there. So you'll display different branches, different commits. It will detect that their like metrics are also stored in your Git repo. It will detect parameters and all the other like DVC associated artifacts. So you'll be able to like sort and figure out which commit or which branch has the most kind of promising results. There's also an option to compare different plots across like different commits or branches. So you can see, for example, how your loss function evolved over time, or how your metrics like were improving as you kept training. So, and the short snippet for it is here. So you go to like studio.iterative.ai, and you can create a view out of a repo. Already done that here. You can, from the view, you can go directly to the original repository. And yeah, so like the table is interactive. You can see where all your data is stored. And as I mentioned, here's the way to compare different experiments, kind of visualizations. And another cool feature is once you have CML configured in your repository, like CI/CD job, you can change parameters directly from the user interface, provide a commit message, and basically trigger an experiment right from Studio. And that actually goes back to what I did at the very beginning of our talk today. So I made a parameter change that triggered a CI/CD job, and we'll go back to it later and see what happened there. And it created a pull request. So this is a commit message that I provided. I changed the learning rate in this case. And then I can look at the results and decide whether I actually want to merge this experiment into my main, into my experiment branch or whatever branch I started off with. So let's go to summary. So as I said, the entire philosophy of basically everything that I'm proposing today is to apply GitOps for to machine learning projects, because we already have kind of defined and proven best practices in software engineering that rely on Git. So we can leverage those. Then full reproducibility of experiments is important. It improves trust and collaboration between team members, and DVC achieves it through both data and code versioning. ML pipelines clearly state dependencies and outputs for each stage. These pipelines save you time when you don't rerun stages that didn't experience any changes. This enables you to iterate quickly, generate like many experiments, compare them, and then cherry pick the best performing ones. And finally, CML's integration with CI/CD tools and cloud platforms allows you to automatically post reports from CI/CD jobs into pull requests or merge requests, as well as easily provision cloud resources to run computationally intensive workloads. So that is it for the presentation I had for today. Before we go into the live part of today's talk, are there any questions there?
Yeah, there is a question about Studio. Is the Studio free?
Yes, Studios has a free tier for up to 2 users. So basically, if you and your colleague want to try it out, let me actually open it in incognito mode. And just to confirm, right. So if you and your colleagues want to try it out, you can use it for free.
Are you sharing something?
Oh, right. I should have shared my screen instead. Let me reshare. New share. Oh, okay. So you can see that.
Still, oh, now it's better. Now I see your screen. Yeah.
Right. So if I go here into the incognito mode, right? So there's a free tier, which is free for up to 2 members. So if you and your colleague want to connect like your Git repository and just try it out, like you're free to do so. All right. So any other questions?
Not about the studio. So there are a couple of other questions, but maybe let's jump into the demo and then we can come back to the questions.
Right. So here's first what I want to show you. Let me zoom in
Can you make it?
bit.
Yeah, maybe a little bit more larger. Yeah, great.
Okay. So here's what I want to show you is, so here's what I started this talk with is, if you have a need to basically experiment on a remote machine that maybe is a lot more powerful than what you have available locally. So we have TPI, and with TPI, it's like a matter of defining a script, and this is like the whole script. So there's some boilerplate here, but there's a section where you define basically what type of machine that you want. Like we have some like predefined machines. This one stands for like a medium instance with GPU. Like you can define an image. I'm using Ubuntu. And then you can define the profile for like whatever cloud you're using. I'm using AWS. Then there's a section for basically whether you want to like store some outputs. Let's say if you're like running a script that saves some metrics, you can define that this is going to be your output directory, and then download directory when the script is done running. And here, like it looks fairly scary, but it's just a few lines setting up the machine. So here I'm like setting up my SSH keys, like installing some dependencies like Python 3, pip. What else is there? And I'm cloning this this repository and installing pipenv dependencies. So, and at the very end, I'm outputting this command. So basically, this is the command that would launch VS Code from. So let me close VS Code and we'll do it live. So basically, in order to launch the script, I would just run terraform apply. I've already done that, and it takes about, let's say, roughly 5 to 7 minutes to provision the machine and run through all the installation steps. Once that is done,
the script is in GitHub, right? And the GitHub link you shared.
So there's a separate Git repo for it that I can share later, but for now I can at least share the link to TPI. Let me send it.
I can share. I have the link to TPI. Okay.
So, and now I can, once I ran Terraform apply, I can run Terraform refresh. This will output like all the logs the TPI generated. You can see that it like automatically configured like VPC images, like buckets that are needed, like all the credentials. So the benefit of using this tool is that you don't have to know how AWS or Azure or GCP works. Like all of that complexity is taken care of for you automatically. Like the only thing that you would need to know is how to configure a machine from scratch, like what dependencies you need to install for your particular project, which is like cloud independent. So now it spits out this command. So basically, open VS Code using a remote interpreter from this machine and use this directory, home Ubuntu magnetic tiles defects, as the root of the project. So now, like that launched a machine. So again, we can confirm here that we are running on a remote machine with this IP address. And yeah, so can you see everything well here?
Yeah, I'm tempted to ask you to do Control Plus at least once, or what is? Yeah, like that. Thanks.
So here we also have a like DVC extension that I showed earlier. So with, actually discard some of the changes I had here. So with this DVC extension, it enables like an additional tab in the source control tool. So basically, with the first, like everyone who uses VS Code is already used to the first section of it, where if you make a change to your source files, it will automatically detect those changes and allow you to create a commit. So similarly with DVC, because DVC, like we think of DVC as essentially Git for your data. Here you can pull and push your data to a remote storage, and the remote storage is simply configured with kind of this config file that lives under .dvc directory. In this case, I'm using an S3 bucket that stores all my data versions. And let's see, let's move it up here. And then the other set of features that I've shown you is the ability to generate different experiments from this DVC extension. So this is the repository that I cloned. So on the experiments branch, I actually generated like a few experiments earlier. And because this is a deep learning computer vision model, like I cannot really generate many experiments kind of quickly here because it would take quite a bit of time to do. But let's do something like very quickly. I mean, we're going to reduce the number of epochs to, let's say, 3. I mean, that obviously going to significantly worsen the performance of my model, but it will at least allow me to basically generate an experiment quickly. So I can do it by changing the parameter in this params.yaml file, or I can simply do it from this experiments tab in the DVC extension. So for example, I'm on my workspace. I can select, I can start typing the parameter that I want to change, which is number of epochs. And I can set it to, let's say, 2. This automatically starts an experiment run. So you can see we've got a new entry in this table, which is in progress right now. And then in the terminal, we can see the DVC started executing our experiment. As I mentioned,
modified the YAML file, right? And run the thing, right? Because I saw in the script, so config equals params.yaml. So I guess the extension goes there and modifies the file itself, right? And then runs the script. Okay.
Yeah, but it only does that temporarily for that experiment only, and then it kind of resets it back. And in the output, we can see that DVC noticed that our data loading part and data splitting part did not change. So it skipped those. Basically, we saved time. And now, so our training is complete. Our 2 epochs are here. So I can see right away that the validation loss and training loss are both terrible compared to what I had before. I mean, that's to be expected after only 2 training epochs. And now we're running evaluation stage. And that should complete in about 10 seconds. In the meantime, are there any questions?
Yeah, so there's a question about the Terraform provider. The question is if you can use Docker file, like if you can base this on Docker instead of Terraform scripts. And
the answer is,
yes.
Well, it's not instead of Terraform, but you can use Docker with TPI. And we have a blog post specifying like exactly how you would do it. It's more like a tutorial, so you can run everything.
So instead of providing this init script in Terraform that you showed us, we can say, okay, use this Docker image, right?
Exactly. So you can do all this setup, everything inside the Docker container, like with a predefined Docker image, and then just pull the Docker image inside the Terraform script, and then do like Docker run whatever you want it to run. So.
So it's still like the concern the person has is that they will have to learn Terraform syntax, but there is no way around this, right? If you want to use this TPI, you still, even with Docker, you still have to use Terraform.
You don't need to learn Terraform syntax, because even in that script that I shown you before, like all the kind of, say, scary looking part,
it's mostly bash scripts, right?
It's all Linux, right? This is the script that sets up everything. There's like really no syntax. Like if you're using a different cloud provider, like you change this field. If you want to change the disk size, like you change like a few fields here. Like
no, you must admit Terraform looks a bit not intimidating, but
it does.
If you want to get into this, right?
That's for sure. It's not like for a novice kind of user, but again, like as in the blog posts that are linked, if you're familiar with Docker and you can do all of this necessary setup, and essentially if you can move all of this part, like scary looking part, into a Docker container, or at least there may be a Docker container that's already has all the dependencies that you need. Maybe it could be like an NVIDIA container with all the CUDA drivers already installed and so on. You can just significantly simplify this part of the script, and basically would be just like pull the container and run the command. So that's kind of the idea. Any other questions?
Yeah, but maybe because that's not the whole thing, right? You have something else.
Yeah.
So let's see what else we have.
What I show you is that at first, if you want to like experiment on your different hyperparameters, like with this extension, you can like generate as many experiments as you want and basically visualize them. Again, I would highlight the main benefit is not having to maintain a separate third-party service and do all of that locally. And then if you don't like the experiment, you can simply like remove it from your local workspace and it disappears. All right, so let's now go back to like how we created our pipeline. So let me zoom in a little bit more. So at first I had this notebook that was processing all the data. I'm not going to go into details, but the idea is that it was basically downloading the zip file. And there's a link. Here's the link to where the data lives. It just downloads the zip file, unzips it, and then does some like pre-processing to that data. And I refactored all of that into a data loading part, which essentially does all the same things, kind of downloads, unzip data, like sorts them into different folders. Like there's images and there are segmentation masks. So most of this refactoring is simply like copy pasting code and creating self-contained functions out of notebook cells. Same goes for like model training. So there's like reading in the data, defining your data loaders, and training your model. For those who are interested, I'm using the FastAI framework here. The main reason is because it's a lot less verbose than using like PyTorch natively. And the point of this demo was not to learn how to do image segmentation, but to show kind of what the end-to-end process would look like. So if we go to the training script, there's a little bit of boilerplate code for reading the parameters from the params.yaml file that I have here. And then finally, like training our model and saving the model pickle into kind of the appropriate models directory over here. And then this is kind of the key part to all these stages, that we make this module runnable from command line. So we accept command line arguments, parse them, and launch this module with command line arguments. When all of that refactoring is complete, we can create dvc.yaml file and basically say, like, for my data loading stage, I want to run Python data load.py with this config file. It depends on the data load file itself. It depends on certain sections of my parameters file. And it's going to output images, like files, into images and masks directories. Same goes, like similar thing goes for like data splitting and training. So I'm running Python train.py. I depend on certain directories and the Python file itself. And I can also log my training metrics. So all of those interactive plots that you've seen, it actually uses another open source project that I forgot to mention. So there's DVC Live, which is an ML logger. So integrates with pretty much all most popular machine learning frameworks that people use, like Keras. Like I'm using FastAI. For Keras, it looks exactly the same. So you import your logger, pass it as a callback to your training function, and then it just logs all the training metrics into flat, like CSV or TSV files. And it's exactly the same for FastAI framework that I used.
So logger here in the sense that it captures all the metrics at each step, right?
Yeah, so it's an ML logger as opposed to like a traditional, software logger.
And you just import it, and you don't need to do anything. It just, I guess, like auto login in MLflow, right? It just gets all the metrics.
Very similar. But the difference is, like instead of sending all of that information somewhere to like a remote server, it logs locally. So you've got like those directories with all the TSV files. Like in this case, I've got like my timestamps. This step is the epoch number, and I've got my evaluation or training loss values in here. So this is how I would create the pipeline. Once my pipeline is created, in command line, I can run dvc DAG. And what it will do is show me my dependency graph. So let me clear and rerun this, dvc DAG. So here's my dependency graph. It's fairly simple, starting with dvc load, dvc split, and then training and evaluation depends on both stages, data split and train. So if I change either the splitting stage or training stage, evaluation stage will be executed as well. And again, the nice thing about DVC is that you don't have to define the dependency graph. Once you define your DVC YAML and basically list outputs and dependencies, DVC figures out the graph for you. Right, I think there were a few questions there, so let's take 2 minutes to address them, and I'll continue.
Yeah, so I'm checking. I see that this deep learning uses a model from, like it uses FastAI. If I use TensorFlow to build the model, what I need to consider here?
Well, the first thing, if you want to replace the framework, it would be essentially like changing how you, like all the training logic, obviously. Basically, you will.
That's mostly this part, right? This train model function.
Yeah, so,
right? So you would need to change that.
Mostly this part, but then evaluation part, you load your model, so you'll need to change that as well. But other than that, it'll all be kind of the same structure at least. And then if you want to log metrics from a different framework, so where's TensorFlow? So there you go. So you just import like different, you do different imports, import different objects from DVC Live.
So DVC doesn't care what you use. It can be TensorFlow, PyTorch, MXNet, whatever.
Not only that, it doesn't care about the framework that you're using. It doesn't even care about the language that you're using. If you want to use R, you can use DVC and create like a similar pipeline in R or Julia or whatever you want to use. So DVC is completely language agnostic.
But if you want to use the logger, right, then you need to use one of the frameworks that is supported by the logger.
Yeah, exactly. That is correct.
Okay, and another question was about MLflow. So like you have this pipeline with DVC, and if you want to integrate MLflow in this, it would be perhaps one of the steps, right? Or I guess you would add the MLflow here in the Python scripts.
I'm not that familiar with MLflow, like to give like specific advice. But yeah, if you want to use, because MLflow also has like different sets of features, right? If you want to use just the experiment tracking feature, I'm pretty sure you can integrate it with DVC pipelines. You'll just be logging all your metrics into MLflow instead of like using DVC Live and in combination with Studio.
So I imagine it would be like you set up MLflow, you configure MLflow at the beginning of this Python file, Python script, and then you do with MLflow, whatever, and then you just have the whole thing here.
Yeah, you put those like decorators or...
They have the with block in MLflow.
Or with blocks,
Yeah, I see no problems here with adding MLflow support to this particular script and in general.
Yep.
Okay, and then there are a couple of people, quite a few, asked to have a step-by-step tutorial showing how to set this up. Maybe this is for a different workshop, right?
Oh, this would be, I mean, like in reality, like a project like this, and and keep in mind, like I'm not even talking about like the fully kind of real world scenarios where you need to think about like security, how you deploy all of that. So this is like a simplified version of a real world project. And this took me like a couple of weeks to build. So I'm showing you like a really very, very condensed version of it.
But I think we can catch up offline later with you, Alex, and see if there is maybe we can do something that have a stripped down version and have a code along session for that. But this is something we can take offline.
Maybe. But in general, like I did start with notebooks, refactored into the pipeline, and now you can either run this pipeline as I've shown you from the DVC extension. So you can create the like different experiments, or if you just want to run your pipeline with existing settings, just reproduce it. There's a DVC repro command. So just like start your pipeline. For example, we just started training. Let me open another terminal. Actually, can I open it side by side? There you go. And I also pre-installed NVTop, which is a command line tool to monitor your GPU usage. So we can see that my GPU is almost fully utilized during training.
Oh, that's a nice tool. I didn't know. Like I usually do watch NVIDIA's on my.
All right. So this is mimics the HTOP interface.
Yeah.
Shows you like how much memory you consume.
But this one is much nicer.
Yeah. So yeah, right now we're running. I'm running my pipeline locally. So this would take like, I know, close to 7 or 8 minutes at least. So I'm going to terminate this.
Yeah, there is a question regarding the experiment management part. So the question is, when you committed the best experiment, the other experiment disappeared. Is there a way to keep multiple experiments for comparison?
Yes. I'm going to link again to the right part of the documentation. So if you can share this link, so there's a whole section on how you would persist different experiments. So yeah, you can generate like 100 experiments, but only persist like, I know, 5 of them or 2 of them or however many you want.
So that was on purpose when it disappeared, right?
Yeah. Like I only wanted to pick like one of them and keep it. But you can either create like have several commits, so one on top of the other from different experiments, or you can create like different branches. So let's say you want, maybe you even you can experiment on different architectures, right, of your model in different branches, and maybe even different frameworks. Like you can have a branch with like, I know, a Keras model and a TensorFlow model, right? So you can experiment on different branches and then compare their performance. So was also a question about CI/CD pipelines, I think.
Yeah.
So here, like at least in GitHub, you define your workflow files under the .github/workflow directory. So you can have as many as you want and configure them like to be triggered and do different things. So for example, I have this like experiment workflow, and like, for example, I don't want it to run on main or the dev branch. I only want it to be triggered when I'm working like on an experiment or like a feature branch. And then there's like some code that basically checks out my repository, configures AWS credentials. This is the part that I've shown you before. So this launches a cloud runner. Like this is the EC2 instance type. And then finally, like in this next stage, I'm installing my dependencies. So this command DVC pool just pulls all the data from the remote storage but it's specific to that commit. So it will pull the appropriate version of the data that I need, rerun the pipeline, and then when you run the pipeline, it will generate like a few files. Like there will be a new file with metrics. There will be a new, like when DVC pipeline is complete, it generates this log file, lists all the like commands that were run, all the dependencies, as well as their hashes. So, and this, where was I? Here. And this command basically keeps track of all the artifacts that were generated. And then with CML, I can tell it to essentially create a PR. So CML PR. I think earlier there was a question like, how does like CML and DVC work together? So this is the idea. With DVC, you create your machine learning pipeline, you version all the artifacts like data and models and so on. But CML allows you to integrate into your kind of Git platform and like CI/CD capabilities that they provide. So we create a pull request. We kind of can provide different options. Like here, I'm using this squash option, basically saying I want to squash several commits into one. And then the last section is creating a customized report, right, to be published under that pull request. So, and that customized report is nothing more than a simple markdown file. So I'm just posting like a header with metrics. DVC supports kind of outputting, printing out metrics in a markdown table format. So if I run DVC metrics show and provide a flag dash markdown MD, and then just redirect the output into the markdown file, so it will create a table for me. And then finally, like here's like a section that is very customized to this particular project. During the evaluation stage, I'm picking like a few, I'm generating some test predictions. So here, for example, I'm taking like a test image, generating the input image. In the middle, we've got the ground truth, and the right-hand side, this is the output of the model. And then inside the CI/CD workflow, as a sanity check, I'm picking 20 random test images like this, and I'm publishing them into this report using the for loop in Bash. And then with the very final, with the very last command, I'm just posting this report into my GitHub repository.
Yeah, there's a question about this. So you don't need to do git push here, right? So this happens.
CML takes care of it automatically.
Okay.
Yeah. So there's another convenience. So CML has the CML CI command, which automatically configures your Git user, like your Git email, a username. It clones your repository like properly so that you can like do all the
and then
kind of
so
Git
you need to
comparisons
provide your token for that, right? So it was one of the configs.
Yes.
Personal access token. This is something you need to get in your settings, right?
Yes, in your Git settings. Let me see if I
and then you put this to your repo, right?
Yeah, and you store it as your
secret.
So here in the if you go to the settings of your repository, and then in the actions, you can define different like access keys, secrets, and so on. So I have like all the AWS related stuff, Heroku API key, and GitHub personal access token. So let's actually go back to like remember.
Yeah, I have a question about this. So I was wondering, like, how does it know that it needs to run on GPU? Because on free GitHub account, you cannot use external runners, right? So how does it work here? Like, first of all, do you use a free account here for actions, or it's?
I think you can replicate it in the free account because there's like some like limited number of
Because I see this
KCD runners
runs
that you
on.
have, but all
Yeah,
the
this
heavy
runs
lifting
on.
is not done by the GitHub runner, right?
Okay.
It's done by the self-hosted runner in AWS. And GitHub runner doesn't care about like the fact that my pipeline needs a GPU to run. Like, as long as I like define that I need a GPU machine here in the cloud type, and then I give it a label, like in this case, like I said, CML runner. In the next stage, I'm referring to the same label. So basically telling GitHub runner that all of the below stuff needs to happen in the, like, there's also a Docker container. So in this Docker container on this remote machine. So the actual GitHub runner doesn't like do any of the heavy lifting.
Okay. Yeah, thanks. Yeah, sorry I interrupted you. You wanted to show
No
us something from the studio, right?
Right. So earlier, when I started, like at the very beginning of the talk, let's see if we can refresh this. So remember what I did? I picked like a commit. I went to the run tab and I changed the hyperparameter. So I set it to 30 instead of 20. And here's what happened, right? In my Git repo, let's actually open it. So I was on the experiment branch. So this is the, okay, where was that? Oh, so if we go into the actions, so this is the commit that I made, set an epochs to 30. That was like almost an hour ago. The job itself ran for 14 minutes. There's here are the two stages: deploying the runner. Like deploying the runner in the cloud, like it's fairly short process, under 2 minutes, and then the whole model training. Because I set it to like a fairly for this data set, 30 epochs is like kind of pushing it. So the whole training ran for like 12 minutes on this GPU instance. But then the nice thing that happened is because of that, let me switch to VS Code. Because of this command, CML PR, so create the PR and also squash it, what happened is Studio automatically created this pull request for me. And you see kind of the direction. So I told Studio that I don't want to make that commit directly into my experiments branch. I asked it to create a new branch. So you have like several options, well, two options here. When you change the parameter, you can either, like you need to provide like some commit, but you can either create a new branch or commit directly to the existing branch. And now in this pull request, I see all the changes that are associated with this experiment of increasing the number of epochs to 30. So this is what I changed in my parameter. Here's how the metrics changed. I can see that both train and validation losses got smaller. Let's actually check the metrics. Oh, so yeah, my dice coefficient increased from 80% to 85%. So this is the DVC log file. So all of these changes are basically, this is what I was talking about when I said like experiment versioning. We're not just managing our experiments, we're versioning them in Git. We have, with CML, we have an additional kind of benefit of seeing the, where's that, the report. I think GitHub like automatically hides it somehow, so I need to figure out where that was. So there should be a report in the pull request. under the comments or okay. Okay, so this is the report that I was talking about. So this is
Where did you find it? I missed that part.
So here it's in the
So it created a
so
PR,
CML.
right?
Yeah. So because I automatically it merges the PR with all the artifacts. So this is the original pull request. This is the one that was automatically merged by CML. So I can see all the metrics and reports in here. But then if I go to my studio, I can see like some of the experiments I committed, basically ran directly on that cloud machine that I'm using for VS Code. So you can see kind of my avatar, like profile picture here. And like this experiment I ran with Studio, like the last two experiments I ran with Studio. So I can see kind of the metrics here. So because I like this PR because it improves my metric that I care about, I basically accept the pull request. Like, let's imagine that we added someone else, like our collaborator from our team. So maybe there's like some conversation going on, and we eventually kind of confirm. I'm gonna trim the message. And we merge this pull request into our experiment branch. From this kind of temporary branch into experiment branch, we can remove the temporary branch. And now Studio detected there were new commits that were available. So we update the view, and there we go. So now let me actually hide this one. So now you can see that there's kind of this new commit with 85% of dice metric. So let me go back. And right, so I think so I hid a few experiments here. So you can customize the view kind of as much as you want. You can like move the columns and like the metrics in here. You can hide specific like branches or commits that you don't want to appear in the view. And you can share it with like, you can make it either public or private and share the link as I did, I think earlier today.
So you did, right? And now if we click on this link, it should show this dashboard.
Yeah, you will see exactly the same view. So if I customize it and save, you'll see this.
I can see it.
Yeah, if I move around the columns like this, so you'll be, basically every time you make a change, you'll need to save the view. Then we also have like plots, so I can compare what I had in my like main branch to what I have now in the experiment branch. On my main branch, I only trained for like 10 epochs, so I got to like this result. But then experiment branch, right now we trained for up to 30 epochs. So I think we got like 5 minutes left, so we can, I think, wrap up with just questions.
Yeah, the question.
Sorry, I should mention kind of one last thing, which is essential. Like when I said, the deployment part is the fact that now when you deploy, you can have a separate CI/CD workflow that basically like you don't even need to rerun your pipeline, right? Because again, with experiment versioning, you can trust that like your experiments are fully reproducible. So you can just pull the specific pickle that you want when you need to deploy. For example, if I want this deployment workflow to only run when I merge something into the main branch. I pull my model pickle, and then I use GitHub artifacts. So this is basically a temporary storage for CI/CD jobs. I can store like this model there. And then in the deployment part, I'm picking up this model from this artifact storage, building a Docker container with this action Heroku deployment. and then deploy it to this endpoint. And yeah, and then it kind of exposes the API so that you can send an image through like curl or whatever. And there's a, I think there's a link in, there's a description here in the README file. We scroll to the bottom. Right, so you can pick like any test image that you want, send it to, if you want to test it locally, there's a Docker container that you can build, or you can try like a live API that is available here and just send the test image. And what it will respond with is a segmentation mask with like zeros and ones showing where the defects are. Yep. And that's all I had for you today.
Are you sure? Is there maybe another YAML file that you want to show us?
No.
No.
Well, I think we're around, because if we wanted to do a dive deep, there's obviously a lot more details and nuances that we
we still have 2 minutes, right? Yeah, maybe just so I see that there is a question. Is there a way to use CML to automatically trigger the CD phase? I think you just showed the CD phase, right? CD is continuous deployment. And this one, the one you show us, is exactly that, right? So when you merge the pull request, will it automatically redeploy, you think?
Right. So it's kind of like really has not much to do with CML, because it's up to you how you want to configure your CI/CD jobs. Like you can be as creative as you want. Like here, I'm just saying, like on every push, like on every Git push, I want to run this workflow, but I also want to ignore branches that are main and dev. You can like run CI/CD jobs for like if you tag something with a specific name, like if you create a tag out of your Git branch, you can run like a deployment job, or you can only trigger CI/CD jobs on like merge requests or approved merge requests and so on. And then inside of those jobs, you can run CML. So it's kind of like CML, it happens like after you configure how you want to run your CI/CD jobs.
So CML is more like, correct me if I'm wrong, so let's say we have a team of people and then the data scientist plays with the parameters and they want to get some sort of approval from others. Okay, this is my experiment, this is the result of the experiment, look at this PR, and then maybe a team member comes and looks, and then they accept, say everything is fine, and then the team merges the PR, right? And then after that, you can configure your CI/CD pipeline, GitHub Actions to actually, I don't know, deploy the new version, right?
Exactly. And that's what I was talking about, kind of already using the existing like best software engineering practices, right? When someone works off of a feature branch, they make the changes, they create a pull request, like a few team members kind of review, they go back and forth, maybe make some edits, and then eventually like they approve the PR, and that goes into like the development branch and eventually into like production. So what we are trying to achieve with these tools is pretty much the same workflow that already used by software engineers.
And I guess for this particular case, we would need to save the artifact, the model, right? So we don't need to retrain it next time we.
Exactly, like and that artifact is versioned by DVC in the remote storage of your choice.
Yeah. You showed it at the beginning, right? So the architecture of DVC, like you have this. Was it a storage, right? So like you can keep it in S3.
Yeah, let's see if we can find it. Let's see.
Yeah, this one.
There you go.
Okay. Yeah, I think that was quite a lot of information, and we see people thanking you.
Yeah, I can imagine.
Love the video. Thanks for the walking through. So that was amazing. Thanks a lot. Yeah, and thanks everyone for
Yeah, thanks
joining
everyone
us, for asking
who
questions.
attended. Definitely check out DVC, CML. As I mentioned, both are NTPI. All of them are free and open source projects that live on GitHub.
Okay, I guess that would be it for today. How can people find you if they want to ask you a question?
Oh, right. I completely forgot about like the intro earlier. But I mean, you can find me on LinkedIn. I guess if you search for Alex Kim Iterative, yeah, so you'll find me there, or I can post a link to my profile, I guess.
Yeah, we have the links, and you have a speaker
Yeah.
profile in Datadog's blog. So if anyone is interested, we have all your public profiles. Okay,
Right.
I guess that's it. Thanks, Alex,
Okay.
for joining us today, for doing
Thanks for
the
having me. Okay. Bye.
presentation. Yeah, goodbye. Bye, everyone.